Now I want to flip the problem and solve the other one. So we saw with a complex pipe, or any kind of turbulent pipe, where we know the pressure and we want to find the velocity, that's a pain in the neck because we have to guess a friction factor, correct it, guess again, etc. But if we have the reverse problem where we're told the velocity and we're asked to find the pressure, that's really easy because we can just simply solve for the pressure based on the velocity, which we have in that form. So we want to see if that same thing is true here. So we already did the harder problem for the pipe network. We wanted to find the required pressure for a particular flow rate, and we were able to show how to do that. Now we want to see, is the other problem easy? And it turns out it's not very easy. So the question now is, how much pressure is needed to make an m dot of 10 kilograms per second with this same pipe network? So we have the same A and B, same length, same diameter, same roughness, same loss coefficients here. So we want to see how we would solve this problem. We can no longer just solve for u, solve for delta p as a function of u because we don't know which way the velocity is going. Is the velocity going through the B pipe or the A pipe? Those pipes have different diameters, so that's going to result in different pressure losses. So we can't do it that way. So we'll see what happens here. So this is the problem. Here's the setup. Here are the equations that we have. The question is, how much pressure do we need to make an m dot mass flow rate of 10 kilograms per second? And here are the equations we have. We have that the mass flow rates have to add up to 10 kilograms per second. So that's with both pipes. So the A velocity times rho times the A area, the B velocity times rho times the B area, those have to add to 10 kilograms per second. Here's the pressure relationship in each pipe. Now again, these are separated from each other. But nonetheless, we need to figure out, what pressure we need to drive this flow to satisfy both this equation that doesn't even have pressure in it and these two equations. All right, so how are we going to do that? The first thing we're going to do, because we learned last time that these friction effects were negligible, basically, almost, compared to these loss coefficient effects. So to make this problem easier to get a handle on, we're first going to assume that those will not be significant. So FA and FB effects are negligible compared to the K values. So that's going to be very helpful because if we can't know UA and UB, we can't solve them directly. We don't know them in advance because even though we know the mass flow rate, we don't know how much is going to A and how much is going to B. So that's going to be a problem because these F's are going to be different. They depend on U. That's going to make it very confusing. But if we get rid of these terms, we'll see that it's not too hard to solve it. So let's go ahead and try it with those two terms gone. So with those terms gone, here's what we have. The pressure drop then is equal to 1/2 rho UA squared times 1.8, just the loss coefficients. And the pressure drop is also equal, that same pressure drop is equal to 1/2 rho UB squared times also 1.8. Now here, if it were different, this wouldn't make any real difference. These things would still, they could be, if they had different loss coefficients, that wouldn't make the problem significantly harder. That would just change the ratios. But at any rate, this is the key. And the other key to emphasize at this point is that delta P is the same for both, right? Because delta P depends only on the pressure at the inlet of both pipes, which is here, and the pressure at the outlet of both pipes, which is here. Those are the same for both pipes. So these delta P's are identical. So we can set these two equations equal to each other. So we have 1/2 rho UA squared times 1.8 is equal to 1/2 rho UB squared times 1.8. And that is pretty good because that means the halves cancel, the rows cancel, the 1.8s cancel, and all you are left with is that UA squared equals UB squared, which of course means that UA equals UB. So that's a huge finding. So UA, in this case, equals UB. Notice that, I want to emphasize again, like that's nice and easy to realize. If these numbers were different, if 1.8 wasn't the same as 1.8, you still would have a very nice result. So that it would not make it harder. Like if this were, 3.7, that wouldn't matter. You would just have a ratio here. You'd have, UA would equal 3.7 over 1.8 times UB. So it would not make the problem harder in any way. But in this particular case, because we said those loss coefficients are actually the same, we're just saying UA equals UB. All right, so given that, we can now go back to the mass conservation equation, which says that UA times rho AA plus UB times rho AB is equal to 10 kilograms per second. And then we say, all right, but we know that UA equals UB. So I'm going to change this to a UA. So I have UA times rho times the area of pipe A plus rho times the area of pipe B is equal to 10 kilograms per second. All right, so then I can solve for UA, and UA is equal to 10 kilograms per second divided by 2.83 kilograms per meter plus 1.26 kilograms, excuse me, I guess per meter also, per meter. Is that right? I think it is right. Okay, yeah. Kilograms per, yeah, that looks good. All right, so there's that. And so then I can say this is a 2.83 and 1.26. So in the end, I end up with UA is equal to 2.44 meters per second. So I've already solved for UA, so that's fantastic. So not a very hard problem. Why would this have been harder if I had had the F's? Well, it would have been much harder if I'd had the F's, because right here, I would have had 1/2 rho UA squared times FA LA over DA plus 1.8 is equal to 1/2 rho UB squared times FB LB over DB plus 1.8. The problem would be I could get numbers for LB and LB over DA and LB over DB, but these F's, I would have had to guess those F's, both of them, and that would have made the problem very, very much harder. I could not have possibly solved for this UA. I would have had to do a crazy kind of multi-step guessing. So anyway, the fact we were able to neglect these F terms meant that this term did not depend on UA and this term did not depend on UB, so we could cancel a lot of stuff and get to an actual answer. So we got to 2.44 meters per second. For that, that allows us now to go ahead and calculate the delta P. So the delta P is equal to 1/2 rho UA squared times 1.8. That's what we started out with. And so we just plug our UA into that, and we get that that equals 5,358 newtons per meter squared. So that's the answer. Delta P is 5,358 newtons per meter squared. I didn't ask you for this, but I wanted to check it myself, honestly. I wanted to know what the hell is UB? Well, UB is equal to UA, so that's 2.44 meters per second. And I wanted to make sure this came out to be the right mass flow rates. So, M dot A is equal to rho AA UA, and that came out to be 6.91 kilograms per second. And M dot B is rho AB UB, and that came out to be about 3.07 kilograms per second. So subject to rounding error, these do add up to 10. So you've got, what do you got there? 9.98. So that's basically 10 with our rounding error. So that does work. So this situation worked. This is the correct pressure to have the problem work, to get the problem if you have the pipes in, a simple pipe system like this, where you have two pipes connected together, flow going in both pipes from the same pressure sources. We can solve both directions. But if we had to solve the second problem, where the pipes were longer so that the friction could not be neglected, so those F terms could not be neglected, had we had to do that, this problem would have been extremely challenging. I don't even know how we would do it, honestly. We'd have to do lots of guess and check in order to, get to the answer in the end.